Hello, welcome to Algebra 1 with Miss Andrea. Today we're going to continue our unit on describing data, which is the 8th module in the online book in the class, which I believe is labeled Unit 6. And it's section B. There's two sections in this module, A and B. We're on the second section, section B. And we're on page 4 of this module, so we're calling it lesson 4. And this is about interpreting and representing two variable data. Let's get started. So we have a table here of data, a frequency table, right? And that's what this information is called. Well, this one isn't a frequency table, but we have a table of data here. And it shows the median age of females in a particular year. And it's given to us, this data is gathered from the US Census. Okay, now the information we have is every decade, so every 10 years. And we need to identify an X variable and a Y variable. Now, using the years as the X variable would cause us, our graph and everything, to just be out of the norms, like a 1970 graph. If you tried to graph that on your calculator, you would have to change the viewing window a lot in order to be able to see that, because those numbers are so huge. So a better fit, not only so that it looks better in the calculator, but so we kind of have a little bit better information, is to think of this as time, because it's the time that has passed. Now, in order to do time, we have to have a base of 0 where we started. And so since our data that we gathered started at year 1970, we're going to say, oops, okay, there we go. Let's say our input, or our X value, and this is going to be our Y value, or an output value. So our X value, or time, T, is going to be time. Our input value is time. So 1970, no time had passed. That's the starting value. So we're going to put 0. Okay, well, in 1980, how much time has passed? Well, our unit will be years. So in years, how many years has passed since 1970? 10 years have passed. Okay, 1990, 20 years have passed since 1970. And in 2000, 30 years have passed since 1970. And in 2010, 40 years have passed since 1970. So you can see how we were able to get our T variable, our time variable, and this is our input, what we generally would call our X value. Input, this is going to be our output, which when graph is usually on the Y-axis, right? And this is age, right? So if we're calling T for this one, we'll call A for age here. So this is going to end up being a function. Normally we have function of X, right? Well, instead of saying function of X, because we're using the variables A and T for age and time, so it's age based on time. Okay, so when we consider the time, what's the median age? Okay, so this is a function of age over time. Yeah. So let's take this data and put it into a scatter plot. Oops. Oh, I wrote on top of the scatter plot. I'm going to have to erase that. My computer is moving extremely slow here. All right, here is your data points. Now your data points have our time here on the bottom for what we would consider the X-axis, and the age for the Y-axis. So the input and the output variables, in our case, it's T and A. And so these are all those points. This is the one that we, the year 1970, it was 0 for our time. This was 1980, 10 years later, 1990, 20 years after 1970. So you can see all this data here. Now, this data is in what shape? Based on all the functions that we studied linear, we studied quadratic, and we studied exponential, right? Those were the 3 types of functions we studied. This graph mostly simulates which type of those graphs? Well, it's going to simulate a linear graph, right? So you can see it kind of would go something like that. And if you notice, there's not going to be a way to get every single line, every single point in the exact same line, because they all have a different slope between them. Okay, so the lines are definitely would be wonky. We wouldn't be able to get every single point and have it in a straight line. It would be a series of different slanted lines if we were to connect the dots, right? So what we need to do is find a line that is the best fit of all this data, meaning it's going to be as close to all the dots that we currently have as possible. And this is called linear regression, or the line of best fit. And it's the line that passes as close as possible to all of the points that we've plotted here, but it doesn't necessarily need to pass through even a single one of them. It's just whatever line is the closest to all of them. Now, we have a formula for that, so that you would be able to determine what that is, okay? Let's see. Here is the formula. Doesn't that look like fun? But wait, don't write it down yet. I've got a little hint for you. When you're doing statistics, usually we have calculators for all these formulas. So you don't need to even write it down or fill it in. You don't need to know what this sigma means. You don't need to know what the capital, X, the linear year, the population size for a given census, number of observations in years. You don't need to know any of this, right? But so let's see what we do need to know. We need to go to something called metacalculator.com. And this is going to be, there are YouTube videos, tutorials for you to be able to do it on your physical calculator. And when you go into a physical school, you will need this. You cannot do it on the computer, but everybody has different calculators. So I'm not going to teach us on the calculator. I want you, if you want to know, and you should know how to use your calculator to do this work. So you need to Google your model number of your calculator and linear regression and how to, and it'll teach you how to do it on your calculator itself. That'll probably be faster than doing it this way on the computer, but also when you're taking your tests in school or standardized tests, you will not be able to use a computer, but you are able to use your calculator. So it's important to know how to do it on the calculator as well. Today, we're going to show you how to do it on this meta calculator, okay? So here we go, metacalculator.com. I have that up right here. And it says, once you go to this website, let's go back to this slide. It says, once you go to that calculator website, you're supposed to choose the statistics calculator. So let's go back to the website. You can see there's all these different calculators to choose. We're going to choose the statistics calculator. Okay, I've done that. Then it says press start calculator. This right here is what you should have written in your notes. So I'm going to press start calculator. Okay, now what do? I choose linear regression and make sure linear is chosen. So when I'm here, I'm going to choose, oops, I typed it up wrong. It shouldn't say linear regression. Regression analysis is what it should say. So make sure you make the appropriate notation in your notes. Instead of saying choose linear regression, choose regression analysis and make sure linear is chosen. Now, if our data was in the shape of a parabola, then we could choose quadratic. There's cubic, there's exponential, there's power, there's logarithmic. There's all these different ways to find a best fit line, but the data we're looking at look like a line. So we're going to choose linear. Now we need to put in our data. Remember, our first year was 0, and I think it was 29.6. Let me see. 29.2. Okay. And 0.2, and then it was 10 years and it was 31.3 maybe. I'm going off memory. 31.3, yay. And then 20, and I know that one's 34 and 30. Let's see what this one is. 36.5. 38.2. Okay, now that we've input all the data, you notice that this is the XI. The I stands for, because remember, X is all of these different ones. And so the I is the 1 or the 2. So X1 is 0, X2 is 20, X3 is X3 is 20, X4 is 30, X5 is 40. So F. So they don't know that we've chosen A and T. So they've defaulted to the standard way of writing functions, which is F of X. And so that's why you see the F here and not a Y, because it has to be a function, right? So F of X. And so the F values are going to be what we have for our A's or our Y's, our output values, as it were. So we filled those in. Now, once you've filled in the data, let's see what it says here. Input data, analyze button. So we're going to push this analyze button right down here at the bottom. And it tells us, let's go back to what you should have in your notes. Equation found in regression equation field, and it's not in standard form. Okay, so the regression equation field. So this is our formula right here. Now it says it's not in standard form. Remember, our standard form is y equals mx plus b. So our mx is here at the end and b is here at the beginning. So it's not in standard form. So we would need to, switch it around. It would be something like y equals 0 to 3 to x plus 29.2. And that would be our formula, right? Now, I have graphed all of these points on Desmos, my calculator I like to use on the computer. And you can see all of the points here, right? And then I've also graphed this right here, if you notice, is that same equation, y equals 0.232x plus 29.2. So we're going to see how close this gets to all of those. And you can see it definitely passes through some of the points, but then other points it is definitely missing. So this is what we call the best fit line. So this line, or the line of regression, this is the line that's going to be closest to all of the data. Now, why do we have this line? What do we do with it? Well, it helps us to determine the information that we don't have in our data. So for example, what about the year 1975? Well, the year 1975 will be right here, halfway between 1970 and 1980. So we can look and say, okay, this would be the best guess answer of the average age of females in that year, right? Whatever that line is. So you can figure out, okay, well, what you can interpret the information and anticipate what the answers are going to be when you have a best fit line. All right, so knowing that, I have a question for us. So we have that equation. I have it, I know you can't see it there, but I have it written at the top. So using this equation that we got from that statistics calculator, we need to make a prediction about the median age of US females in the year 2020. So 2020 is our input information, but remember, we can't input the year 2020. Our input information is the time since 1970. So if 2020 is 50 years after 1970, we need to put our input value of t equals 50. Because remember, this isn't really y. I know that's what our calculator told us. This is a of t. And this right here is t. Okay, so when we input t, we're going to input it here into this t slot. Okay, so that's what our step 2 is, substitute into the equation. So we're going to put a of t is 0.232 times 50 plus 29.2. And we have to plug this into our calculator. 0.232 times 50 plus 29.2, and I get 40.8. A of 50 equals 40.8. So I used a different equation to calculate when I got 39.2. I rounded these to the nearest tenth. So it was just 0.2 instead of 0.232. So you can see how rounding really will change your answer. 39.2 is much different than 40.8, right? So rounding really does make a difference, and you need to pay attention if your teacher or the material on the test or the quiz or the homework tells you to round to a specific place. You need to make sure to do that. So our conclusion is, using the data, we can predict that the median age of females in the US in 2020 will probably be close to, I'm going to put 40.8. And even 40, if you wanted to round, you could round to 41 because that's pretty close to that. But as you can see, that's going to be a much more accurate answer because we had 0.232 instead of just 0.2. So 40.8. All right, so now you have an opportunity to try these yourself, but please notice that it just says 0.2 on here. It wasn't the full equation from before with all of the to the 1,000th place. I've rounded here to the 10th place. So make sure you use that in your equations when you're filling them in. You have two questions here. Approximate the median age of the US females in 2015. And when will the approximate age of the US females be? 42. All right, pause the video, go ahead and work that out on your own, and then unpause it when you're ready to go over it. Welcome back. So the approximate median age of US females in 2015. Again, this is going to be our input value. And our input value is not exactly this. It's not exactly the year. It's the year, how many years have passed since 1970. So 2015 minus 1970 is how we're going to figure out how many years have passed. 2015 minus 1970 is going to be 40 years. That can't be right. 45 years. I don't know why I looked at that wrong. 45 years. So we're going to put in our equation A of 45 is 0.2 times 45 plus 29.2. And let's see what we get. And we get 38.2. So we can say that A of 45 is 38.2 as the best guess answer for the median age of US females in the year 2015. All right, so when will the approximate age of US females be? 42. Well, 42, remember, the age is our output year. The A for age is our output year. So when will 42 equal 0.2t plus 29.2? How many, we want to know how much time will it take to get to be that 42? Okay, so we have to solve for this. And so we're going to subtract 29.2 from both sides. So 42 minus 29.2 is going to be 12.8 equals 0.2t. And then what's happening to t is it's being multiplied by 0.2. So we're going to have to take that 12.8 and divide by 0.2. And you get 64. 64 equals t. So is it the year 64 that this happens? No, it's 64 years after 1970. So we have to do this one extra step and do 1970 plus 64. All right, so 1970 plus 64 is 2034. So our answer is in 2034, that didn't take well. The approximate age of US females will be 42. All right. So now you know how to interpret the data, use the best fit line or linear regression in order to find some answers to help you interpret some data and predict. And that's all statisticians do, is they predict things into the future. They use the data they already have to figure out predictions. All right, so I've got some practice for you. I want you to use that calculator that I showed you and input all of these datas and get me the regression line or the best fit line for the data set. Okay, and I want you to round to the nearest 10th for each of the following. So the calculator that I gave you rounds to the nearest 1,000th, but I want you to round to the nearest 10th. Okay. So go ahead and pause the video and get that done. All right, welcome back. So instead of me inputting all the data and you watching me use the calculator, I've gone ahead and just done it, and you can check your answers. So y equals 6.4x plus 0.4. I input all of the hours and the number of free throws, and this was the answer. So miles logged on the treadmill versus the weight. And you can see that this is a negative number. The more miles they ran, the lower their weight was. So y equals negative 0.6x. That's why there's a negative there, because this is going down as this goes up. And it plus 211.4. Here is the latitude of a city and the average annual temperature. Okay, so let's look at this one. It's y equals negative x plus 99.7. So that negative x means that we had a negative 1 point something as our coefficient. I think it was negative 1.001. And we rounded to the closest 10th, which would be negative 1.0. And so that's the same thing as negative 1. And a 1 as a coefficient disappears. And the negative has to stay, but the 1's going to disappear. So that's why we just have negative x. All right. So that's it for today's lesson. Go ahead and do your practice work, and I'll see you at the next lesson.